All right, welcome everyone. I'm really excited to tell you about Marin, which is a radically new way to develop AI models. So this couldn't possibly be a better venue to give this talk. If you look around us, you see PyTorch, Jupyter, Git, Docker, all of these open source tools we all use in our daily lives, right? So it's very clear by now that open source software is a spectacular success. There's a HBS article from 2024 that estimates $8.8 trillion worth of value has been saved by businesses by using open source. Now, it wasn't always this way. If you look at the history of open source, it has been a bit non-monotonic. So the idea of openness, and this goes back to the 50s with MIT hackers and people thinking about open science. And in the very early days, it was open. Software was open, hardware wasn't. And in the 80s, when software became commercialized, things started getting closed off. And that's when the open source movement started happening with towering figures like Richard Stallman or Linus Torvalds really paving the way for this new generation of open source software. And then in the late 90s and the 2000s, that's when a lot of investment came into the space and open source software became what it is today. Now, I would like to argue that AI in 2025 is where software was in 1999 with respect to openness. So now, if you look at AI, for much of AI's history, up until the end of the 2010s, there was open research. People published papers. If you look at all these papers, these are the foundations by which modern AI systems are built. There were a lot of open data sets and frameworks being spun out in the 2010s as well. And this led to the ability for anyone to really get involved in open research and AI. But then in the last 5 years, while we celebrate the successes of increasingly capable AI systems, we also see that openness has plummeted more and more. Until today, the most powerful AI systems, we don't know how they work and we don't have really insight into them. So there's a sort of interesting parallel here, right? In software, it started open, then it became closed, and then against sort of all odds in some sense, a miracle happened that open source software reigned supreme. And now AI, we are sort of at the cusp. It started open, it became closed, and I would like to argue in this talk that there is a path towards making AI truly open. So what is open source AI? This is a term that gets thrown around a lot, and often I think it's misconstrued. So on one hand, you have some folks saying, Meta being open source, doing open source AI, and then other folks saying that, well, the Meta Llama license is still not open source. So what does open source really mean? So I think this is a really important thing to get right, so I want to break it down a little bit. So there's many levels of openness. So first of all, closed is clear. So closed models are ones that are available only by API or through a product. Then you have open weight models. These are models where the weights are released. You can go download them, you can use them, but you don't know where they came from. This is akin to releasing a binary executable in the case of software. And of course, in that, in the software case, you wouldn't say Microsoft Windows.exe is open source. Then you have open source, where the weights are open, you can see the code, you can see the data recipe for producing the model, and so on. But I want to go a little step further, because I don't think we have yet seen something that really captures the spirit of open source. And I like to propose that we think about open development. And in open development, the weights are open, the code and data recipes are open, and more importantly, you can see the process of the development itself. And this has an important implication because anyone can audit and they can contribute, and it becomes a much more of a community effort. So this is what Marin is about. And just to kind of hammer this point in, Open development enables a community to actually gather around it. And this is the true spirit of open source. So this, if you can read it, this is the Linux GitHub repo. And anyone, all of you can go submit a pull request and contribute. Well, Linus might reject your pull request, but that's another story. So the mission of Marin is to open and advance the science for training frontier models. So let me tell you about how Marin works. So what does it mean to build a frontier model? There is a huge design space of possible things that you have to figure out. You have to figure out the model architecture, the loss function, what optimizer, how you're going to do the learning rates. There's a bunch of systems level things, how you quantize, how you parallelize kernels, how you fit the scaling laws so that you can do experiments at small scale and go up to larger scale. Data is a huge effort. How do you curate, transform, filter, do synthetic data, and so on. And then not to mention reinforcement learning, how do you align the models, do safety, and so on and so forth. So there's a huge design space. But if you boil it down, what the model development process looks like is this. There's a bunch of experiments that are run. Each experiment picks one of these things or a few of these things in the design space and sees if you can make it better. Better means more reliable, more efficient, higher accuracy. And if it works, it gets merged into the main branch and life continues. This is obviously a simplification, but this is at a high level how the development works. And now if you look at this, you say, well, this isn't that different from how software development works, which means that maybe we can just leverage the infrastructure that we've spent decades building for open source software and do it for AI model development. So this is how Marin works. We use GitHub issues, not a new technology. So the idea of a GitHub issue is that you pre-register an experiment you're going to do. I'm going to test, for example, this architecture versus architecture, another architecture. And then a pull request against the GitHub issue is essentially writing down what the actual executed experiment is, which might involve multiple runs. This experiment gets executed, and then the results are visualized using Wampi or whatever you want. So if you go on to marin.community, you can see all of this. I'm not going to have time to do a live demo, but you can click on this link and go check it out yourself. But I'll walk through an example. So this is one example of a GitHub issue according to an experiment where we were comparing a mixture of experts versus dense models. And so you start with a hypothesis or a goal, and then there's a pull request that is actually, we designed this simple, you can think about it as a DSL that allows you to write down the full experiment pipeline in Python. So it's reproducible. You can see every single hyperparameter, what data is used and everything. There's no mystery of of the provenance. And then when you run this Python program, it generates a full trace of all the way from the raw data to all the steps in tokenization and to the actual model training and evaluations and so on and so forth. So it gives us complete transparency into how a model is built. And this is, I think, I'm just very excited because then you can start to begin and do science on these things. So I'm going to talk about three aspects of Marin here. One is that it is a platform that allows you to develop models, but how do we use it? So we've been doing a bunch of research on Marin itself, and that's the science part. So you ask the question, what is the best optimizer? So there's been a flurry of different optimization algorithms that have come out in the last few years. All of them claim some sort of remarkable speed up. So we said, okay, let's actually benchmark it rigorously and see. And we found that, well, even though there are some improvements, many of the improvements, if you sort of vanish from 40% to down to 10% at model scale, there's also a lot of things that you have to do right, like tuning the hyperparameters. And Marin allows you to have this rigorous platform to do this study. Here's another question. what is the most data efficient training algorithm? So as compute grows, high quality data is growing less quickly, and we need better and better methods that can generalize from small, high quality data sets. So this is another experiment we did on Marin, where we looked at standard training, and then we looked at even very simple things like tuning the hyperparameters better, using regularization, doing some ensembling, and in the end we were able to get a 5x data efficiency win over standard training. So which means that you need 5 times less data to achieve the same level of accuracy. So there's another pillar of Marin, which is once we have our best understanding of science, we just go out and train some models, because there's no substitute for actually just trying and seeing what happens. And here is the principle we have is that we never look back. That's why I guess it's YOLOing. So last year, we set on an expedition to train an 8B model from scratch and see what we could do. And there were a bunch of stages during the training. There's an excellent retrospective that David Hall, the tech lead on the project, wrote up. And I encourage everyone to read it. This is really an honest account of how model training works. It's not, we released the model and look how great it is, but this is an honest take of all the mistakes we made. And there were a lot of things that happened. If you see this loss curve, it doesn't look good. We managed to fix it through some experimentation. But in the end, we got an 8B model trained from scratch that beats the Llama 3.18 base on the majority of standard benchmarks, which we're quite proud of. Earlier this year, we started training a 32B dense model. And all of this is open development. So we regularly, I tweet out, here's what's happening. You can go on the Discord, you can figure out what's happening. And if you see a curve that looks like this, some people said it's fine, and some people said it's a little bit worrisome. The thing is that the loss spikes here, the model actually does recover. So maybe it's not a big deal. Sometimes you get sick, and then you get better, and then you go on with your life. And furthermore, the loss was going down. Things were looking great. It was way outperforming the 8B. And then one day we rammed into a bad spike. The loss did not recover. And we said, OK, time to really do something about it. We tried a bunch of things. It didn't really work. And then finally, we begrudgingly added this thing called QK norm, which people have done, but we thought we were too good for. But ended up fixing the problem, and there was smooth sailing from there. So that was the journey of the 32B model, and we ended up with now the best open source, not open weight model. So we're still trying to catch up with Quen 32B, but I think it was not bad for the first 32B run. So I've told you about the things that we're doing, but I think one of the main selling points of open development is that we can get all of you involved. So let me tell you about that a little bit. So as I mentioned before, we have an open Discord channel. Anyone can join. And we talk about what we're doing, what runs we're doing, new papers that come out. We're trying to debug why this experiment isn't working the way it is. And it's a growing, it's a growing community. We also have a leaderboard, since everyone likes a leaderboard. So it's like, OK, I'll give you a leaderboard. But this is a different type of leaderboard. This is not the standard benchmarks where you come with your model and we don't know how it was trained and we're going to just evaluate it. This is a leaderboard for methods, which means that you come with your model architecture or learning algorithm, or eventually we'll have data sets as well. And we run your models on an increasing set of scales. And then we fit a scaling law. Because one of the things that we've learned through model development is that things that work well at small scale don't necessarily work at large scale. So embracing scaling laws early on and looking at the slope, not just the absolute intercept, is key to making sure that the methods that we merge into main are actually good. So this is a point where the community can come with all their best ideas, and Marin can be a hub where all these ideas shine. So in conclusion, I've shown you a radically new way of building models. It's not just open way, not open source, but actually open development. And it might seem radical, but if you just reflect on the way open source software works, that's already what we're doing. And look at the successes that we've had with open source software. So let's work to build the Linux foundation models together so we can see that have the same thing replicated for AI models. With that, thanks.